Welcome back to Part 2, Sorting. Given an array or collection of elements, our goal is to reorganize it so that the elements are in some order. This could mean either ascending or descending order. You can order numbers or strings in any natural way. Or you can order objects. For example, objects that represent students. You could order them by last name, first name, or you could order them by GPA or class rank, etc. There are dozens of sorting algorithms. We'll only take a look at one and focus mostly on how to sort properly in JavaScript. Selection sort is a very simple sorting algorithm that works as follows. First, you iterate through the array and find the smallest element. Once you've found the smallest element, you swap it with the first element in the array. Now the smallest element is sorted. It's where it belongs. So you repeat this process on the remaining n-1 elements until it's sorted. Let's take a look at a demonstration. Here we have an array of elements that needs to be sorted in ascending order. We'll iterate through the array and find the smallest element 1 and swap it with 13. Then we'll iterate through the array again and find the next smallest element, which is going to be 2, and swap it with 3. We iterate through the array again to find the next smallest element, but it already happens to be 3, and so 3 is swapped with itself. Iterating again, we'll find 4, 5, 6, etc. After each iteration, the ith element is in place. Selection sort requires about n squared operations, where n is the size of the array that you want to sort. There are many other sorting algorithms, such as insertion sort, quick sort, merge sort, tim sort, and many others. Slow sorting algorithms, such as selection sort, require about n squared operations. Consequently, if you were to double the size of the array that you want to sort, that would quadruple the execution time. Fast algorithms, such as quick sort, merge sort, and tim sort, all operate using about n log n comparisons, or operations. Doubling the size of an array using n log n operations roughly only means that you only need about twice as many operations. In other words, fast sorting algorithms scale as you increase the size of your array. We won't go into the details of any of these fast sorting algorithms. Instead, we'll simply want to use what's already available to us. In software development, it's rarely good to reinvent the wheel. It's preferable to use the built-in sorting and searching functions that are provided by the language or framework that you're using. In JavaScript, we have a function called sort that's associated with any array. The problem, however, is that the default behavior is to sort lexicographically. For strings, this is fine. It'll sort A to Z. For numbers, however, this comes out wrong. Let's take a look at a demonstration. Here we have an array of strings: Jolene, Irene, Roxanne, Cecilia, and Lola. Let's go ahead and call the sort function on it. When we do, names is now in order. Cecilia comes before Irene, then Jolene, Lola, and Roxanne. They are sorted in alphanumeric order. Now we have an array of numbers: 8, 2, 9, 4, 100, and 3. However, when we sort it, it's not in order: 100, 2, 3, 4, 8, and 9. This is because it's sorting in lexicographic order. 100 starts with 1, so it would come before 2, even though it represents a larger value. If you were to sort these numbers alphanumerically, this is what you would expect. But it's not what we want. We want it sorted so that 100 comes last. The solution is to use a callback to define the ordering. The sort function knows how to sort, but not necessarily how to order. That's why it uses the default of lexicographic ordering. We'll use a callback that takes two elements, A and B, and returns a number indicating their order. It'll return something negative if A comes before B. It'll return 0 if A is equal to B. And it'll return something positive if B comes before A, or A comes after B. A callback function like this is called a comparator. Let's take a look at an example. Here I have the same array of numbers. We'll call sort, but pass it a function that takes two arguments, A and B. The sort function will actually use this function to determine whether or not two elements are out of order in the array. We need to provide the logic for ordering them. So let's go ahead and write it. If A is less than B, then that means that A comes before B, and we should return something negative. we'll simply just return -1. Else if A is greater than B, then that means that B comes before A, and we should return something positive. Otherwise, the only other case would be if they're equal, so we'll return 0. When we execute that, now it's in the proper order that we would expect. This is a lot of complex logic. We had 3 if-else-if statements. We could greatly simplify this by looking at the difference of the two numbers. A minus B. Now if A is greater than B, then A minus B will be positive. If A is equal to B, then A minus B will be 0. And if A is smaller than B, then A minus B will be negative. So we can simply return it and get the same result. By providing a comparator callback, you can have as complex of logic as you want. If we have an array of students, for example, we could implement logic that would compare based on the last name. And if the last name, and if 2 students shared the last name, Smith and Smith, it could then look at the first name. By using a callback, we can make our comparison as complex as we need it to be.